Hello, chemists. This is Ms. Placino, and you are watching Lesson 2.6 on quantum mechanical electron configuration. In today's lesson, we're going to talk about how the electrons are going to fill the different energy levels and sublevels within an atom. If you're not familiar with the terms energy levels and sublevels, you might want to backtrack to Lesson 2.5, which was an introductory lesson on quantum mechanics. In today's lesson, we're going to have a couple of things to take care of. We're going to be able to apply and explain the Aufbau Principle. The big one for today is writing electron configurations using the quantum mechanical model for atoms in the ground state. And then towards the end of the lesson, we're going to show you a shortcut to writing out these complete electron configurations. And the shortcut is called the noble gas configuration. As you get more confident in writing electron configurations, you might want to switch to the shortcut to save yourself some time. All right, lots to do today. Let's get started. The Offbot Principle. Basically, this just states that electrons must fill the lowest energy levels first. We kind of applied this with the Bohr model of the atom. We knew that we had to put the electrons as close to the nucleus as they could be, and only once those low energy levels filled up could we move further away. That's easy in the Bohr model when you just have those concentric rings. But things get more complicated with a quantum mechanical model. We know that the different sublevels have different shapes, and some of the sublevels have multiple orbitals present. So trying to figure out which ones are the lowest in energy and where the electrons will fill first tends to be confusing for new chemistry students. Luckily, there's a little chart that we can use to help us figure out how to put the electrons into the atom. So you have this in your notes, the numbers 1, 2, 3, etc. Those are representing the different energy levels. Hopefully you know S, P, D, and F. Those are the different sublevels. As we make our way from the top to the bottom, we see an increase in energy. And hopefully this makes sense. We know the 7s, for example, is larger and farther away from the nucleus than the 1s. To complete this chart, we're going to start drawing more arrows. So we've got this arrow going through 1s. We're going to draw another one going through 2s and keep that at the same angle as that first arrow. And we're going to just continue to do that for all of the energy levels and sublevels, just going through and kind of skewering all of them. So go ahead and do that. So if we follow the arrows from the top to the bottom, starting with the 1s, that's going to start to line up our first energy level and sublevel to be filled, and kind of just go from there. When we reach the end of an arrow, you just move on to the next one. So I'll try to write neatly, but I'll show you what I mean. So according to this filling chart in the Aufbau Principle, we'll start with our lowest. There we go. Energy levels and sublevels, and we'll make our way to the highest energy levels and sublevels. So we'll just start with that 1s. Okay, nothing else on that arrow, so let's look at the next arrow, 2s. That arrow is finished, 2p, 3s. Okay, next up we've got 3p, 4s. We're just going to continue on with that. So if I'm finished with that arrow, I go to the next one, 3D, 4P, 5S. Then what do we have? 4D, 5P, 6S, 4F, 5D, 6P, 7s, not all gonna fit, 5f, 6d, 7p. Sorry for kind of wrapping it around. I couldn't get it to fit. I wrote too big. There we go. You're rarely up until past the 7s anyhow. Okay, so this is the tool we can use to predict how the electrons should fill the different energy levels and sublevels, going from the lowest down with like the 1s up to the highest with the 7p. I'm going to remind you that this is just a tool to predict. This is not some absolute rule, and it probably goes without saying, the electrons are not aware of this filling chart. They don't necessarily behave this way, but this works out for most of the elements on the periodic table, so it is a really helpful and useful tool. Okay, let's try to write an electron configuration applying the Aufbau principle. Let's look at sodium. If you find sodium on the periodic table, you'll find that it is atomic number 11. We're only going to be writing electron configurations for atoms. So sodium, with its 11 protons in the nucleus, will have 11 electrons. We want to start trying to figure out how those electrons fill the energy levels and sublevels. So if you think back to what you just wrote for with the Aufbau principle in the filling chart, we're going to start with our lowest energy level and sublevel first. How many electrons can we put in the 1s sublevel? Well, every s sublevel has one s orbital, and every orbital holds 2 electrons, so I can hold 2 electrons in the 1s sublevel. Now it's full. I can't put anything else in there. I have to go up to the next one, which happens to be the 2s. What's the maximum number of electrons I can put in the 2s sublevel? Well, it happens to be 2 again. You can always max out any s sublevel, regardless of the energy, with just 2 electrons. All right, after the 2s comes the 2p. There are 3 different p orbitals within a p sublevel. So what's the maximum number of electrons that we can hold in a p sublevel? 2 times 3 gives us 6. Put a little superscript of 6. It's good to go through and just kind of check in and make sure that you're not overdoing it with electrons. I've got 2 plus 6. All right, that gives me 10. Where does my last electron have to go? What energy level and sublevel? We would predict to see it in the 3s. And I know in math class, if you don't write a little exponent of 1, it's assumed that there's a 1 there. When it comes to writing electron configurations, you're going to include the 1. Please don't just write 3s and assume that someone's going to know that there should just be 1 electron in there. And there it is. That's the quantum mechanical electron configuration for sodium. Get my sort of messy handwriting out of the way so you can see it more clearly. Just to kind of break it down, those coefficients, the big numbers, if you will, in front of the letters, that's the principal energy level. We know the s's and the p's in this example represent the sublevel. And finally, the exponents or the superscripts tell us how many electrons are in that particular sublevel. Let's look at a couple of practice problems. And in your notes, you are asked to write the full quantum mechanical electron configuration for phosphorus, manganese, and strontium. So I would suggest pausing the video and try these out. To save you a little bit of time, I've told you how many electrons are present in each. All right, hopefully you've taken the time to figure these out. Let's check your work. Phosphorus with its 15 electrons should have this configuration. 1s2, 2s2, 2p6, 3s2, 3p3. You can always kind of just double check, make sure that you've got the right number of electrons by quickly adding up the exponents or the superscripts. And in this case, yes, you've got them. That's 15. We'll drop down to manganese with 25 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. All right. Hopefully we're 2 for 2. Strontium with 38 electrons to contend with. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. More often than not, you can kind of usually just check like the last couple of energy level, sublevel, and number of electrons. And if those agree, there's a high likelihood everything else is in agreement as well. You might have noticed already, even though this is only like the 4th electron configuration that you've written, that things get really, really repetitive. If you're wondering, man, isn't there a shortcut for that? There absolutely is, and we'll talk about it later this lesson. So don't worry, you won't be writing out full configurations forever. On the next page, there are some practice problems for you to play around with. If you were in class, I would tell you to kind of split up the work with a neighbor or two. Take some time and write out electron configurations for the elements that have been grayed out. They're the list below this table. I would go through and try to do at least half of them, and then we'll come back and we'll kind of start talking about applying electron configuration to the periodic table. So pause the video, try to write out some of those electron configurations, and we'll come back and talk in just a minute. Okay, so you can see that I've started to fill out the periodic table. Hopefully you've gone through and wrote some electron configurations for the grayed out elements, and you were basically told to write like the last term of the electron configuration, so sublevel, energy level, number of electrons in that element's box. Also, in your notes, this was already started for you. Okay. What I want you to do is start filling out the rest of this table. Not all of it. I know that is kind of overwhelming, but if we just kind of start filling things out based on the Aufbau Principle or that filling chart that we took a look at earlier this lesson. So I have 1s2, 2s2, it's filled. Next up would be like the 2s1, then I can have 2s2. That fills up the s sublevel. I got to move to the p's. So 2p1, 2p2, 2p3 we already got, 2p4, 2p5, 2p6. Fill out as much of that table as you need to until you start to see a pattern. And some of you might see it right away, some of you might take a little bit longer. That's okay. So go through, fill out what you need. We're going to spend more time dissecting the periodic table next unit, but there are still like kind of some patterns and trends that we can observe without being super knowledgeable of the table. As you're filling stuff out, you should be thinking about what sort of patterns you see with the sublevels. Kind of even just with what we've got right here, you might have noticed that the sublevels kind of clump together. Your S sublevels tend to be over on the far left side of the periodic table, with the exception, I suppose, of helium. Your P's clump together, your D's, your F's, so maybe you picked up on that. If you see what happens as we go across the period, and periods are these horizontal rows, we see that an electron gets added in, and like your S and your P sublevels have the same principal energy number. And finally, as you go down a group, and groups just are the vertical columns on the periodic table. So like the second group is a pretty good one to look at. They're very similar, 2s2, 3s2. You'll probably guess 4s2 and 5s2 for calcium and strontium respectively, 6s2, 7s2. So we've got like very, very similar last terms written in the box. If you try to go through and make predictions for the boxed elements, so we've got like Ti, for example, has a box around it. Try to make a prediction about what those electron configurations at last term, energy level, sublevel, and number of electrons would be. So I'm going to go through and do that just in a different color ink. I would expect this one to be maybe 4s1 for potassium. These are definitely 3Ds. I bet titanium is 3D2. That's what I would predict. Kind of make our way across that period. Krypton, so that's the 2p, that's a 3p, it's probably a 4p. And I've got 6 for neon, 5p6 for xenon. Yeah, it's probably 4p6. Technetium, that's a 4d5. Indium, 3p, 4p, this is probably 5p1. Done. Iridium, 5D, well, probably 5D7. That's what I would think. 6P3 for bismuth. Kind of rounds out the main group of the periodic table. All right, so these are F blocks. This is probably 4F. If this is 7, maybe 8, 9, 10, 4F, 11. 5F, 7, 6, maybe 5F5 for neptunium. That's what I would predict, just given locations on the periodic table. take a second to kind of explain how you are able to predict those configurations. I'll pause it, write something down. Yeah, based on the periodic table, things are really organized. I can see that there are what a sublevel is going to be present. I can see, the Ds. I know there are a total of 10 D electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups, 10 vertical columns. So things kind of fit together nicely. I know that my D sublevel comes in with the third energy level. So this must be 3D, 4D, 5D, 6D. There's a lot of ways you can make predictions just strictly based on location. We've kind of been talking about this. Our S block is the leftmost two columns. Our P, well, that's going to be groups 13 through 18, everything over here. Our D, this chunk in the middle, the transition metals. And our Fs are the ones that are offset from the table at the bottom. The last question asked you to connect it to reactivity. If you studied the periodic table maybe in middle school and you talked about families of elements, you might know about the reactivity of one of the groups. So I'm not going to go over this one right now, but if you learned about reactivity, try to make a connection between that and the electron configuration. And my guess is, just to jog your memory, maybe it was alkaline metals or alkaline earth metals or halogens or noble gases. Look at the electron configurations, recall some general properties or some reactivity in particular from those groups, and try to draw a connection. Okay, so I want to wrap up today's lesson with noble gas notation. You've probably written enough electron configurations by now to notice it is very, very repetitive and it can be time consuming. So the noble gas notation is a shortcut we can use to save ourselves a bunch of writing. Actually, I'm going to go back to this page for a second. If you look at the noble gases, those are group 18 elements: helium, neon, argon, krypton, xenon, radon, and oganesson, which was fairly recently synthesized. You probably noticed, well, with the exception of helium, everything is 2p6. Argon would be 3p6, 4p6, 5p6. We're filled through the p sublevel of that energy level. So we're going to go back to the previous noble gas, so the one that came before the element we're trying to write the electron configuration for. We're going to put the symbol of the noble gas in brackets, specifically square brackets. So I do something like that. Then we're going to write out the remainder of the electron configuration as you normally would. Basically, by putting the noble gas in the square brackets in an electron configuration, something like neon actually means 1s2, 2s2, 2p6. That's all summarized just by square brackets around neon. So this can save us a lot of writing. You can use any of the noble gases in square brackets. If you're asked to write the electron configuration of a noble gas, you cannot just put it in square brackets. You have to go to the one behind it or previously on the periodic table and go from there. So let's go back to phosphorus, manganese, and strontium. So this is hopefully what you wrote for the electron configuration of of phosphorus. If you go back to the previous noble gas, that would be neon, which basically we can pull out those first three terms and just write neon, 3s2, 3p3. Manganese. What noble gas would we use in this case? We definitely have past neon. Hopefully you're thinking argon. And argon, by putting it in square brackets, summarizes those 5 different energy levels and sublevels. Argon, 4s2, 3d5. Strontium, oof, so much writing. We can definitely go past neon, we can go past argon, yeah, we can get all the way up to krypton. Krypton, 5s2. If you're thinking, well, wait a second, I had to write out all of that configuration in order to condense it down, how is that saving me time? Well, if you use the periodic table to predict configurations, you wouldn't end up writing all this stuff down. I'm not going to require you to write in the shortcut. I've found over the years that I've been teaching that students who like to use the filling chart tend to prefer to write out the entire electron configuration, even though it is more time consuming. And students who like to use the periodic table to predict configurations, they tend to prefer using the noble gas notation. Either way is perfectly valid. You can express the electron configurations in terms of both, and they're, again, both equally correct. So don't feel bad if you prefer to use one way over the other. As long as you're correctly making the predictions, I'm going to be happy. All right, that wraps it up for today. Thanks for tuning in, and I hope you found this helpful.